Hi everyone, welcome to this video on acid-base reactivity trends. Let's dive right into it. So, as a quick review, let's go over what acids and bases are. Acids donate H+ ions or hydrogen ions, while bases want to steal those hydrogen ions. So, some examples of acids are hydrochloric acid, ammonium ions, and carboxylic acid. Some examples of bases include amine, alkoxide or hydroxide, and carboxylate. So notice how all of the acids have hydrogen atoms. At least one hydrogen atom that is ready to be donated. And the bases will want to steal those hydrogens. For example, if we take alkoxide, this O- will want to steal that hydrogen, and the electrons that form the bond between hydrogen and chloride will all go to chlorine. So to understand acid-base reactivity trends, we need to go over some vocabulary. So all of the red words are synonyms of each other. They mean the same thing, which is to say, if, for example, some acid, let's use HCl, is very reactive, that means it's very unstable, it has high energy, and it's a strong acid. On the flip side, if we deprotonated HCl, which just means took away the hydrogen proton, then we would be left with a chloride ion. This chloride ion would be a weak base. It is unreactive, very stable on its own, and low energy. So it is a weak base. Weak bases do not particularly want to steal protons. However, strong bases really want to steal protons. So they are a lot more likely to be in an acid-base reaction. One way to tell if something is a strong acid or strong base is to look at a pKa table. So pKa is a number that tells you how strong or weak an acid or base is. As you can see, to the top of this table, pKa starts at the lowest values. And the lower your pKa value is, the stronger the acid is. So strong acids have very low pKa values, while weak acids have higher values. On the flip side, conjugate acids have the opposite trend. So if you have a very low pKa, that means your base is very weak. So as you can see, we just went over that chloride ions are weak bases. If you have a very high pKa, that means you have a strong base. And just to note, they use acid and conjugate base because if you react HCl with some base, I'm just going to call it base, and this base uses its electrons to attack the hydrogen proton, then you would be left with Cl-, which is the conjugate base, and hydrogen bonded to the original base, and this is the conjugate acid. So this was acid, base, conjugate acid. So it can be a little bit confusing, but just remember that the acid, when it's deprotonated, it becomes a conjugate base, and a base, when it gets protonated, becomes a conjugate acid. It's more easy to tell which one is which when you see, oh, the product conjugate acid has hydrogen, so it has to be an acid, like it gained hydrogen. while the conjugate base, it lost a hydrogen through the reaction, so now it's more likely to be a base that wants a hydrogen back. Now you might be asking, what is the cutoff for what is deemed as a strong or weak acid or base? And my teacher taught us to use the cutoff of 15 pKa. So anything above this line is a strong acid, and anything below this line is a weak acid. And same goes for everything above is a weak base, and everything below is a strong base. Your teacher might say something different, so make sure to pay attention to what they say. Alright, now for formal charge. So formal charge is one of the biggest determining factors of acid-base reactivity. Let's say we have this acid. Our question is, does a positive or negative formal charge give us a stronger acid? And we're going to see that the positive formal charge gives us the strongest acid. So this molecule is the most acidic, while this molecule actually isn't even an acid because it does not have hydrogen in it. So this would be the weakest acid because it's not even an acid. Even if it counted as an acid, the negative formal charge would make it a very weak acid. Now, why do the charges determine acidity? Because this positive nitrogen really wants to give away a hydrogen so that it can gain more electrons. If we had some generic base and we reacted it with this molecule, you can see that nitrogen would take all of the electrons that was forming the bond between it and hydrogen, and it would become this molecule, which is more stable. And as we talked about before, more stable means less reactive. Less reactive means weaker acid in this case. Let's do a base example. Let's look at these molecules. Which one is going to be the strongest base? The strongest base is going to have the more negative formal charges. So it's going to be this molecule to the right. And at the left, this is the weakest base. But wait, this is not even a base because it already has so many protons that it can't steal anymore. These trends should make some intuitive sense because acids want to become less positively charged and bases want to become less negatively charged. Plus formal charges make stronger acids and negative formal charges make stronger bases. All right, now let's look at electronegativity. So based on our Gen Chem knowledge, we know that the most electronegative atoms are in the top right corner. If we want to go from least to most electronegative, it would be an arrow like this. This is least electronegative. I'm just going to write ZF for short. And this is the most electronegative. The more electronegative the atom connected to your hydrogen is for a base, the easier it is to deprotonate that hydrogen. So what does that mean? Let's say we have an acid, hydrofluoric acid. Since fluoride is super electronegative, this is going to be a strong acid. If we took a less electronegative atom, such as oxygen, maybe if we had water, for example, this would be a weaker acid than hydrofluoric acid because oxygen is less electronegative than fluorine. So hydrofluoric acid would have a very strong dipole. So the hydrogen would be super positive and want to get deprotonated by a base, while in water, the dipole is a little less strong. So the molecule is less reactive in acid-base reactions. Now, what about the size of our atoms? Fluorine is smaller than bromine. Bromine is a big atom. And when you have a big atom, it spreads out any of its charges. So that means bromine would have more of its negative charges spread out, while fluorine would have its negative charges very compact and squished together, very dense, and that makes it more unstable. So then fluorine would be a stronger base. It would be more unstable because all of those charges are so concentrated and packed together that it really, really wants to be protonated. And as we saw earlier, if you have a stronger base, then it's the opposite story for an acid. Stronger base, weaker acid. For bromine, it's the opposite. If you have the charges spread out, then your atom is more stable and less reactive. So this would be a weaker base if it's just the bromide ion. Sorry, I should clarify. This would just be the fluoride ion for the stronger base part. And for HBr, that would be a stronger acid than hydrofluoric acid, because weaker base correlates with stronger acid. All right, let's talk about orbitals and hybridization. So if you have some bases that are sp3 hybridized, sp3 hybridized, sp2 hybridized, and sp hybridized, you're going to get different results. To illustrate this, let's draw out the energy levels for these different scenarios. So if our carbon nucleophile, which is this part, if our carbon nucleophile was unhybridized, it would have this energy level diagram. You can see that the s orbital is lower energy than the p orbitals. If you have sp hybridized orbitals, then there is this kind of halfway point where the hybridized sp orbitals lie. So they are higher energy than s orbitals and lower energy than p orbitals, kind of in the middle. So I'm going to write 50%. For sp2, it's more like 1/3 of a difference. So I'm going to write 1/3. Maybe fractions would be easier. So I'll just write 1/2. And then for sp3, it's more like a 3/4 difference, where all of the sp3 hybridized orbitals are between p and s, but because there are more p orbitals, there were 3 originally, so the p orbitals get 75% of the weight. So that's why it's higher rather than lower. And energy is like this. Higher energy is higher on the diagram. So as you can see, sp3 orbitals have the highest energy out of all of the hybridized orbitals. sp is here, sp2 is here, sp3 is the highest. So that means sp3 orbitals provide the strongest bases. Higher energy equals stronger whatever you're looking at, and we're looking at bases. So how would hybridization relate to acids? Just think of them as opposites. Since sp3 orbitals gave us stronger bases, that would mean they gave us weak acids. And for sp orbitals, you can think, oh, since these are weaker bases, they give stronger acids. All right, now let's talk about resonance. So I'm gonna give 2 examples, one with acids and one with bases. For the acids, let's do a cyclohexanol, and a benzylic alcohol. So I'm going to give you the pKa values of each. This one is 15 and this one is 10. Which one is the stronger acid? I'll tell you the answer in 3, 2, 1. Remember that lower pKa values give you stronger acids. So the resonance stabilized acid is going to be more reactive. Why is this? It's because resonance spreads out negative charges. It spreads out electrons. There can be more places that electrons can go, and that makes more stable bases, because bases deal with negative charges. So resonance always gives you weaker bases and stronger acids. Now let's talk about inductive effect. Inductive effect is when some of the electronegative atoms on a molecule create dipoles, and that affects acid-base reactivity. So let's look at this example. Alright, we have 3 molecules here. Some of them have a bunch of chlorines. This one only has 1 chlorine. So my question is, how does chlorine affect the dipoles on these molecules? Carboxylic acid, it has dipoles within itself, but since they are the same on each molecule, I'm not gonna really worry about them. So let's ignore those. Let's just look at the differences between these molecules. So chloride will create a small dipole here between it and this carbon, and that is going to affect the pKa of this molecule. The pKa of carboxylic acid is originally 5, but this middle molecule is going to have a pKa of 3. So the chloride made this molecule more acidic, a stronger acid. Why is that? Because the chloride ion is pulling more negative charge toward itself, leaving more positive charge for the other side of the molecule. So there would be more plus energy there, and this side would be more negative. Now, maybe you can predict what I'm going to say for this rightmost molecule. Since there's so many chloride ions connected, the dipole is going to be even bigger, and this dipole is going to be even stronger. So I'm going to write a very big delta plus. And this molecule is going to have a pKa of 1. So for inductive effect, look for electronegative atoms that will pull negative charge towards them and create dipoles, because that can lead to your molecule becoming a stronger acid. So inductive effect, the more inductive effect you have, the stronger acid you get, or a weaker conjugate base. Since resonance and inductive effect are very similar, a question that might pop up is, which one is stronger? What if you have a molecule that has both? Or you're comparing 2 molecules, one has resonance and one has inductive effect. So whenever this question pops up, remember that resonance is always stronger, because resonance is dealing with moving formal charges around and bonds around, just moving the electrons around the molecule, while inductive effect is only dealing with dipoles. So these are only partial charges. They aren't as strong. So resonance is going to be stronger in determining whether something is a strong acid or weak acid, strong base or weak base. And that's it. So hopefully this review helped you out. If you have any questions or suggestions, please leave them in the comments below. Thanks for watching.